Good day, everyone. We are the Pathfinders. Ever wondered how math can help fight diseases? Sounds interesting, right? Today, we're diving into a super cool topic on how cold graph theory can actually help us predict and stop outbreaks right here in the Philippines. This entitled From Nodes to Outbreaks, Quantifying Disease Vulnerability with a Weighted Graph Approach. The Philippines continues to face major public health concerns such as one is the rapid spread of diseases, especially airborne diseases. In the Philippines, airborne disease like COVID-19 and influenza can spread quickly across communities and it can be a serious problem if it doesn't take proper solutions. Another is the increasing number of tuberculosis cases. Tuberculosis or TB is a serious infectious disease affecting the lungs, remaining a growing concern in several regions. Next is the pneumonia as one of the killer diseases. Pneumonia is another type of airborne disease and is one of the leading causes of mortality, especially among children and the elderly. And the ongoing cases of COVID-19 in the country. Although the pandemic has eased in many areas, COVID-19 cases still persist and require ongoing attention. How can graph theory help? Graph theory can provide a mathematical framework to identify vulnerable areas and assess the potential spread of diseases. Let us discuss the key concepts used in this approach. One is the graph theory. A graph is a model composed of nodes or vertices and edges or connections between nodes. In our context, each node can represent a location or such as a city or a province, and edges represent possible paths for disease transmission. A weighted graph assigns a numerical value called the weight to each edge. Next is the degree centrality or weighted degree centrality. Degree centrality measures how many connections a node has. In simple terms, it shows how central or influential a location is within a network. So here's the formula. For equation 1, the degree centrality of node V is equal to the degree of V. For equation 2, the degree of centrality of node V is equal to the degree of V divided by 1. A higher degree centrality indicates that a region is highly connected, making it a potential hub for disease transmission. Next is inverse distance weighting or IDW. Inverse distance weighting is a method used to determine the strength of influence between two locations based on their distance. Here's the formula. The weight between 2 points is 1 over the distance squared or distance raised to power p. This formula implies that closer regions have a stronger connection and higher influence on each other. We apply these graph theory concepts to study the spread of 3 major diseases in the Philippines: tuberculosis, pneumonia, and COVID-19. To evaluate risk levels of regional vulnerability, we derive a specific formula. For the weight between region I and region J is equal to the number of disease cases in region I multiplied by the population density of region I divided by the square of the distance between I and J. In simple terms, the closer two regions are and more cases and population density in region I, the stronger the influence or weight on region J. And for the centrality of node I is the sum of weights of the edges between node I and all its neighbors J, where Ni is the set of neighbors of node I, and W sub ij is the weight of edge between nodes I and J. In simple terms, it adds up how strongly node I is connected to its neighboring nodes. We can calculate it using Microsoft Excel for better accuracy.
So here, we will see the results of this study that we conduct. The result will show the weight of each edge. First, we use the map of the Philippines as a basis to create its network model. Next is, this study developed a spital network model to assess the vulnerability of Philippine regions to tuberculosis, pneumonia, and COVID-19 by quantifying the interregional influence of disease spread. The model uses inverse distance weighting or IDW and degree centrality to compute connection strengths between regional pairs. Specifically, IDW weights are calculated by multiplying a region's cases by its population density and dividing by its geographical distance to another region. These weights represent the potential influence of one region has on another in terms of disease transmission. After determining individual weights, the degree centrality of a region pair is computed by summing the weights of all its connections, and the results of the computed centrality will be the weighted edge of each region to one another. High centrality values indicates regions that are heavily interconnected and thus more critical in the spread of diseases. The highest centrality for tuberculosis was observed with the paired region of Region 4A or Calabarzon and the National Capital Region or NCR at 123,363.80. For pneumonia, also in Region 4A and Region NCR had the highest score at 82,127. While COVID-19 saw the highest centrality between NCR and Region 4A at an exceptional at 3,144,154. These findings reflects the region's high disease cases, dense population, close proximity, and strong interregional mobility. Overall, the approach transforms raw epidemiological data into actionable spatial insights by visualizing the country as an interconnected web of regional influences rather than isolated units. Using graph theory, we get the weighted edges of each region, and by that we create the network model of each transmittable disease. In the Philippines, on the first image, we can see that it is the weighted graph of the pneumonia. Next is the weighted graph of tuberculosis, and lastly, the weighted graph of COVID-19 as a transmittable disease. Continuing to the conclusion of this study analyzed the vulnerability of Philippine regions to pneumonia, COVID-19, and tuberculosis using a spatial network model that does not rely on individual troubles or mobility data. By employing a weighted graph approach, specifically inverse distance weighting or IDW, and degree centrality, these researchers evaluated how regional dynamic influence the spread of airborne diseases. In this model, regions were represented as nodes and their interconnections as edges, determined by factors like population density, geographical proximity, and historical disease.
For the recommendations, based on the study, we propose the following. One is to inform policymakers. The weighted graph model can help identify high-risk regions that require immediate attention. Another is enable faster response. Knowing which areas are most vulnerable allows for quicker deployment of medical resources and containment measures. Next is improved health planning. This approach can enhance long-term planning for public health and disaster preparedness. And lastly, function with limited data. Even when detailed mobility or contact data is unable, this model provides useful insights into disease spread patterns. These ideas spark more than just solutions. They spark hope. Hope for quicker responses, smarter strategies, and safer communities. With the power of graph theory, we're not only fighting disease, we're creating a healthier tomorrow for every Filipino.